Also, we have seen how to calculate the strength of that welded joint by considering the strip of that welding and how to calculate the area of that strip, so that one can calculate the load carrying capacity, that is nothing but strength of that welded joint. And in that case also we have seen various types of welding joints and how to calculate the strength of that various types related to the welding. Now next part, this we have covered, that is axially loaded unsymmetrical welded joints, and in that case also we have calculated the strength, that is nothing but load carrying capacity, in which we can calculate the equivalent length and all other parameters related to the this eccentric loading. Okay. Now next part is that we are going to see one example related to that, and then afterwards we'll go further. Here you can see the statement, this problem statement I will read. Okay. So in the statement it has been stated that a 200 by 150 by 10, that is 200 length, 150 width and 10 millimeter thickness millimeter angle is to be welded with the steel plate by fillet welds as shown in figure. Here it has been shown. If the angle is subjected to static load of 200 kilonewton, this is loaded as a 200 kilonewton. Find the length of weld at the top and at the bottom. That means we have to calculate LA and LB. The allowable shear stress for the static loading may be taken as a 75 megapascal. That is, the allowable shear stress of that welding is 75 megapascal, and just we have to calculate what will be the length of that weld. Okay. Now here it has been given that A plus B, that is nothing but total width, is equal to 200 millimeter of that angle. This is 200 millimeter, whereas the P, that is load which is applied axially, is 200 kilonewton, that is 200 into 10 raised to 3 Newton. Allowable shear stress is 75 megapascal, that is 75 Newton per millimeter square. Now we consider this LA as a length of weld at the top and LB as a length of weld at the bottom. And L will call it as a LA plus LB. Okay. Now this is the schematic diagram of that stated problem. Now in this diagram we can see we have to calculate LA and LB, or if it is possible we'll calculate LA plus LB, and from that we'll calculate LA and LB by considering any one. Okay. Now we'll take the thickness of that angle as a 10 millimeter. It has been stated in the problem. Therefore, the size of weld which we have to calculate, S is equal to 10 millimeter. And later on, we will calculate the T, that is nothing but is there any problem? Sachin Kengar. Sachin Kengar, can you unmute yourself? Hello, Sachin Kengar. Can you unmute yourself? What is your roll number, Sachin Kengar? Hello? Can you hear me, Sachin Kengar? Okay, later on I will come to know. So when we are going to calculate this T, that is the throat thickness. Okay. So we have to calculate the parallel weld, and the formula which we have derived for the parallel weld is that the P is equal to 0.707. Yes, that is nothing but the T, throat thickness, and L, that is the length, total length of that weld into shear stress. That is, stress is equal to force divided by area. Area which we are going to consider is the T into L. That is the throat thickness into length of that total length of that weld, and allowable shear stress is tau. So when we are going to
आज राजू अकेले ही दिख रहा है ना आया हुआ.
hello, in between somebody is sharing or unmuting himself. Gnaneshwar, hello. Please do not unmute yourself, as and when I am not going to ask you for the unmute. Now, Gnaneshwar, can you unmute yourself?
Yes, sir.
Ha, right now you are unmuted.
Hi, yes, sir.
No, you are now unmuted, but previous to that also. We heard that some other noise also.
No, sir, I am not unmuted.
Here, the person who is going to unmute himself is blinked over here. Okay, by mistake it may have happened, but
Oh, okay, sir.
for all others, please mute yourself, and when required, you can unmute for asking question, or if you have any doubt, or when I'm going to ask you. Okay. So when we are going to calculate the shear stress of that well, that will be calculated, and just we are going to calculate this L total length of that well, and it is coming as a 377 millimeter, 377 millimeter, or LA plus LB is 370 millimeter. Now we have to just find out LA and LB. Okay. Now we have to find the position of centroid of that axis, and then afterwards we can take the movement about that centroid, and later on we can calculate LA and LB. Okay. So let B be the distance of the centroid from the vertical axis. Okay. And that B can be calculated as 200 minus 10. If you are going to see the diagram, this diagram, when we are going to consider this distance A and B, B is the distance of that centroid from the lower position. Okay. And from that, we are going to calculate this 200 minus 10, 10, that is nothing but this thickness of this angle, into 10, that is we are going to take movement about that centroid, into 95. 95 is nothing but, again we are going to subtract that length of centroid. Okay. Plus 150 into 10 multiplied by 5 divided by 190 into 10, that is nothing but area. So by means of calculating that, which you have learned in AME as well as in applied mechanics, that how to calculate or how to find the centroid, and for that we require what, the formulae by means of which we can calculate the centroid. Okay, so that value which we are going to calculate for the centroid is 55.3 millimeter. And once you are able to calculate that B, that is nothing but the distance from lower side, you can calculate A, because A is nothing but 200 minus that whatever may be the length. I'll take this diagram for the reference on the next slide. Okay, so this B we have calculated as a 55.3, and A can be calculated from the higher end, 200 minus this 55.3. So this A and B we have find out, that is nothing but we have located the centroid. Now we know that at the centroid, what we are going to do is that we are going to calculate LA, because LA is calculated by means of these two formulas, that is LA into A is equal to LB into B, and L is equal to LA plus LB. From these two formulas, we have derived LA and LB in terms of L and A and B. So that we'll use here, and we'll calculate LA. LA is L into B divided by A plus B. So LA is calculated as 104.2 millimeter. Now LB, just we have to subtract from the length, total length which we have calculated it as a 377 millimeter. So 377 millimeter minus 104.2 millimeter, and it is 272.8 millimeter. So LB also is calculated, and that is the length of weld which is required to sustain the 200 kilonewton load on this angle. Okay, any doubt?
No, sir.
Okay, then we'll go further. We are going to consider the case of eccentric loading on the welding joint, because we have seen this eccentric loading in case of bolted joint, and in that case we have calculated how to find the dimensions of that bolt. Now here also we are going to consider such situation where the eccentric loading is created on that welded joint. So eccentric loading is going to give rise for both type of loading, that is bending in that welded joint as well as tensile or shear in that welded joint. For that, what we are going to do is that we are going to use these two theories, that is maximum normal stress theory and maximum shear stress theory. This maximum normal stress theory, that is nothing but when normal stresses are exceed, this welded joint is going to break. So in that case, when welded joint is subjected for the bending as well as for shear, bending is nothing but basically it is a compression or tensile. But if it is subjected for the bending stresses, then the maximum principal stress is calculated as sigma max is equal to bending stress by 2 plus half of the bending stress square plus 4 of the shear stress square. From this formula, we can calculate the maximum principal stress which will get induced, the maximum normal stress which will get induced in that weld, and this stress we have to take for the design. And by means of this stress, we can find out the dimensions of that welded joint. Okay. Next, when we are going to consider that the welded joint may get failed because of the shear, basically it is going to subject for the bending and shear. So we have to calculate the maximum shear stress, and this is maximum shear stress theory. In this case, maximum shear stress is given by half of the under root sigma b square, that is bending stress square, plus 4 of the shear stress square. Okay. Now we will consider these two theories, and we will calculate the strength of that welded joint. Now we will consider one case first of all, where P joint is fixed, okay, and one end is subjected for the eccentric loading. That is nothing but the point which has been shown here. On that point, the load P is applied. Now, in this case, this is the what we can say front view, and this is top view. Actually, this black part doesn't mean that we are going to have separate joint, butt type of joint here. No, this is not a butt joint actually, but this is the front view and this is the top view. I can put here for this diagram. So this is top view and this is front view of the same diagram. Okay, and load is applied vertically downward direction, and in this case we have to calculate the strength of this welded joint by considering the welded S is the size of that weld, okay, and T is the throat thickness, and L that is the length of that welded joint. What we are going to calculate the strength of this welded joint. Now, if suppose this T that is the load which is acting at a distance E, okay, from the welded joint, so it will create bending moment as well as it will create shear. So bending moment which will be created in this joint is in this nature because of the load P. This bending moment will be generated, and shear which will be generated, that will be the direct shear in this welded joint. Okay, so we'll calculate the bending moment as well as bending stress and shear stress first, and later on we will calculate the maximum principal stress, that is nothing but maximum tensile stress, and maximum shear stress. We will check it for the both. Now this direct shear which will be created and bending stress which will be generated because of the bending or eccentric load, and that will be equal to P into E, that will be the bending moment, right? So here we want to calculate the throat area, that is the welded area. It is throat thickness multiplied by length of that weld. So it is T into L multiplied by 2. Now 2, because from both sides we are going to use this weld. If it is used from upper side only, we'll take only T into L. If it is used from the bottom side only, then we will use T into L only. Okay. As the welding has been done from the both side of that plate, that's why 2 is used here. So T into L into 2, that is 2TL is the area of this welding joint, okay, which we are going to take for the calculation. Now, if you want to write it in terms of S is equal to what we can say is T divided by 0.707, or T is equal to 0.707 into S. So we'll write this term in S also. Okay. Now, shear stress is calculated as force divided by area. So area which is undergoing for the shear is this upper side of weld, because lower side will not undergo to the shear because of the load which is applied. Okay. So in this case, we are going to calculate the area, total area which will be undergoing for the shear. So this tau is equal to force, that is P which is applied, divided by, in terms of S, 1.414 S into L. Okay, here we have to calculate S and L values. Now this shear stress is considered, and maximum for this is designed for the maximum stress. Likewise, we can calculate bending moment also. Sigma B is equal to, here I will write, which basic equation we can use, M divided by I is equal to sigma B divided by Y. Sigma B divided by Y. So by means of this equation, we can calculate value of sigma B also, and this sigma B is given by sigma B is equal to M by I. Here you have to consider this I moment of inertia which you are going to take for the welded section only, that triangular section. That moment of inertia we are going to consider, and Y is nothing but the distance from the uh, neutral layer, okay, or upper layer or maximum what the thickness of that welded joint, and that will be T by 2. You can understand that it will be T by 2. Okay, so is equal to into Y, M by I into Y. So by means of this, we can calculate sigma B, and later on one can calculate this maximum bending okay. Now by means of these two formulas, we can calculate this sigma B tau, and we can use this equation for which we can calculate maximum normal stress and maximum shear stress. For both these cases, we can calculate the thickness of that weld, that is throat thickness, as well as length of that weld. Now, second case we are going to consider for the eccentric loading. In that case, this plate is subjected for the eccentric loading. Plate, now you can see this is the front view of that plate, one vertical plate, and second one horizontal plate is welded to this vertical plate. Okay, and this horizontal plate is loaded by means of load P and at a distance E. Okay, from the centroid. Now here you can consider this G. G is nothing but the centroid of this area. Okay, this welded area. Now this centroid, how to calculate this centroid, that is shown in this table that we'll see later on, how to calculate the centroid of all these type of joints. If the only one type of weld is lap joint is used, vertical lap joint, then horizontal parallel, two lap joints are there. Okay, two welded parts are there. How to calculate CG for that all type of joints, that we will see in that table. But here you can consider that the CG of that weld, total weld, okay, and that is considered at G. Now here this eccentric distance is measured from this CG, and that is equal to E. Okay. Now due to this P, direct shear will be created and bending stress also will be created in this welded joint. Bending will be created like this. Okay, and shear, because of the load which is acting P in vertically downward direction, shear will be occurred in this welding strip and in this welding strip also. Okay, so this case will become combined stressing, that is bending as well as shear. Now we have to use same principle, that is maximum normal stress sigma T max or maximum shear stress tau max. From that we have to calculate the thickness and all other dimensions of the this welded part. Okay, so this direct or primary stress which we are going to consider here is the shear stress tau, and bending stress. First of all, we'll calculate the direct shear. Now this direct shear stress is given by load divided by throat area. Throat area is 2T, 2 because two strips are used, T into L. Okay. Now if you want to put value of this T in terms of S, it will be 0.707 S. So 2 into 0.707, it will be 1.414, and that's for 1.414 S into L. Okay. So this direct or primary shear stress we have calculated. Next, since the shear which has been produced due to the turning moment, okay, that is T, which is equal to P into E, that is bending moment which is created. It will also create the shear in that well, and that will call it as a tau 2. Okay, and this tau 2 which we are going to calculate, that is the shear, direct shear, which because of the eccentricity, the tau 2 is acting perpendicular at each point, okay, at each point of this well, which we are going to draw from the CG. And that shear stress which we are going to consider, that shear stress which is created in this all welded joint, if you are going to take this tau 2, that is the shear stress which is generated, or movement about this CG of all the forces which are acting because of the eccentricity, that movement should be zero. Otherwise, what will happen? If the movement will not be zero, this will be in unbalanced condition. Now, if the load P is sustained, that is nothing but movement is not created, any motion is not created, it means that the point at which we are going to take movement about the CG, that should be zero. Sorry for disturbance. So moment at G of all these forces which are acting, that should be equal to zero, that we have considered, and by means of that we can write the equation, that is the tau 2 divided by R2 is equal to tau divided by R. R is nothing but the radius and distance from the CG or to the forces which are generated in the welded joint. Okay. So that is constant because the movement about CG is equal to zero. So this tau can be calculated as tau 2, that is shear stress, total shear stress is equal to tau 2 divided by R2 into R. If you are able to measure one distance, and that can be measured because CG already we have calculated, and from that CG we can calculate the distance of the point, this A point, this distance can be calculated, and later on it can be summed, and the average distance of each point from the CG can be calculated. For that, we are going to use this tau 2 divided by R2 into R. Now this tau 2 is the shear stress at the maximum distance, and R2 is the maximum distance from the CG. Okay. And tau is the shear stress at any distance R where you want to calculate it. Now considering, now design has been done always for the maximum shear. Okay. Now by considering a small section of the weld having dA as a distance, or this A point which we have considered, that small distance, because it is going to vary with respect to the distance from the CG. That's why dA will consider as a small area at a distance of R, okay, from the CG. And this later on can be integrated for calculating total shear. So the shear force which is acting on that, that will be tau shear strength multiplied by area, that is dA. Okay. And this turning moment on this shear or of this shear force which we have calculated, that turning moment will be tau into dA, that is the force, multiplied by radius, that is the distance from CG, R. So force multiplied by distance, and that can be calculated because tau already we have derived as a tau 2 divided by R2, tau 2 divided by R2 we are going to put here, multiplied by dA, that is small area, multiplied by r which is present here, and this r, this will become r square. Now this will be the movement of that small welded area dA. And if you want to calculate the total movement, that T is equal to P into E, and that is equal to the total movement which has been created, which has been restricted because of the weld. Okay, so integration tau 2 divided by r2 into dA into r square. Now this tau 2 and r2 are constant. These are the distance of maximum or the point which is having maximum shear stress. And dA is the variable. We are going to take the whole area, and r is nothing but the distance of that dA from CG. So r is also variable. So here we are going to take this a into r square, that will consider as a j, polar moment of inertia of that throat area, okay, about CG. Now here we are going to calculate that polar moment of inertia about the CG of that total welding section. Okay, so that will be calculated here. Now when we are going to consider this bending moment as well as the shear stress, so shear stress due to the turning moment is calculated as T, that is M bending moment, into R2, that is the distance of maximum shear stress where it is generated, divided by J. Okay, so this value tau 2 from this equation where we have just derived it, tau 2 is equal to R2 we are going to take to this side and J to the this side. That's why the shear stress, maximum shear stress, is calculated in that welded part. This shear stress and direct shear stress, that has to be combined together so that we can have the total shear stress which will be generated in that. So in order to find out the resultant stress, the primary and secondary shear stress are combined together. Okay, and these are combined by means of this Cosec law. So tau A, that is the shear stress at a point A, which will be maximum. One can calculate at any point, but we have to calculate the shear stress at point where it will be maximum, and this maximum shear stress will be created at the point which is far away from the CG. Okay, so this is calculated as tau 1 square plus tau 2 square, that is primary shear stress square plus secondary shear stress square, plus 2 tau 1 into tau 2 multiplied by cos theta. Okay, where this theta is the angle between tau 1 and tau 2, that is primary shear stress and secondary shear stress, and normally it is calculated as R1 divided by R2. R1, that is the smallest distance from the CG of any welded point, and R2 is the maximum distance. Okay, of this point A. Any question?
No, sir.
Okay, no problem. Now, how to calculate the polar moment of inertia of all welding sections, that has been mentioned in this table. Okay, this table can be referred, but it will not be provided to you at the time of examination. This we have to by heart. So when we are going to calculate the polar moment of inertia about this point, CG point of this square, sorry, rectangle, then it will be, you know, that BD cube by 12. Okay, so B is the thickness and L is the D, that is nothing but depth here it is considered, and strength of weld is calculated in horizontal position. That's why it is taken as a BD cube by 12, that is T into L cube by 12. Likewise, if the vertical rectangle is there, if two parallel rectangles of welded joints, okay. Now here we are going to consider only these welding strips, and we are going to calculate the polar moment of inertia of that strips. about the CG. Now these are the what we can say regular shapes. But if the irregular shape is there, then it is difficult to calculate this CG. For that, you have to divide that irregular shape into regular shape, and then afterwards, you first of all you calculate CG, and then afterwards polar moment of inertia. Now, when vertical strips are there, how to calculate it? For total rectangular type of welding, how to calculate it? L type of welding, inverted L. A C type of welding, if we are going to connect the C channel to a plate, and if we are going to connect any rod to the plate. For all this how to calculate CG and polar moment of inertia, that has been mentioned here. You can refer this table and you can calculate it. Now this is one example. Okay, such type of examples we in our syllabus it has been not asked. So, but we will see one example by means of which we can calculate the strength of this weld, which is of eccentric type of category. Okay, I'll read this statement. A welded joint as shown in figure is subjected to an eccentric load of 2 kilonewton. Find the size of weld if maximum shear stress in the weld is allowed as a 25 megapascal. Now P has been given as a 2 kilonewton, that is 2000 newton. Eccentricity distance is given as a 120 millimeter. L, that is the length of that plate or weld, is given as a 40 millimeter. Tau max, that is allowable shear stress, maximum shear stress, is given as a 25 megapascal, that is 25 newton per millimeter square. Now S is the size of weld, T is the throat thickness. Now this joint which has been shown in figure will be subjected to direct shear, primary shear, which we are going to call it as, that is due to force P, and that P force is 2000 newton, and then later on bending stresses due to the bending moment of this force multiplied by this eccentric distance, that is P into E. Now this throat area is calculated, or area which is encountered for this bending moment as well as direct shear, is calculated as 2 into T into L. So T is calculated as 0.707 of S. We'll keep this S as it is, which we have to calculate later on. So L distance is given as a 40 millimeter. That's why it will be 56.56 S millimeter square. Okay. So this area, in this area we have to calculate S. Now direct shear which has been generated, that is force divided by area, direct shear stress, 2000 divided by 56.56 into S. So direct shear stress will be 35.4 divided by S Newton millimeter square, and bending moment which is created, which we have considered as a T, bending moment P into E, that will be equal to 240 into 10 raised to 3 Newton millimeter, and this polar moment of inertia Z, or sectional modulus Z, which we have to calculate for this type of welding. From table you can take it. Now this type of loading is there, that is TL S L square. Yes, here we have considered as a thickness of that weld, L square divided by 4.4242. So you are going to put the value of L 40, and it will be in terms of S, and that is 377 into S millimeter cube. Okay, that is section modulus. Now this bending moment is calculated as M divided by Z. You know, Z is nothing but I divided by Y, section modulus. Okay, and that bending moment or bending stress is calculated by means of bending moment divided by section modulus. and that will be in terms of years again. We know that maximum shear stress is calculated. Maximum shear stress tau max is equal to 1/2 of bending stress square plus 4 of shear stress square. That is maximum shear stress theory. In this case, we are going to put the value of bending moment as well as shear stress in terms of years. And allowable shear stress, that is maximum shear stress, is 25 into 10 raised to 25 Newton millimeter square. 25 megapascal it has been given. So we'll keep this 25 as it is, and we can calculate this years. That is the here size of the weld, this size of the weld, and later on we can calculate the throat thickness also from that if required. And that S is equal to 12.8 millimeter, the size of weld which we have to keep as a 12.8 millimeter. Any question? Hello? Do you have any question?
No, sir.
Okay. Now we'll stop here. Only this riveted part, that is again introductory part is there of the riveted joints. That we'll see to the next lecture, and we'll be in position to finish this total syllabus.